Saludos everyone, thank you so much for the invitation to talk to you today about our recent publication where we studied the radar bright features at the North Pole of Mercury using new Arecibo S-band radar observations. The observations were carried out during the summer of 2019 over 6 nights, during which we collected delayed Doppler images of Mercury. An example of one, which you see here. I am highlighting the radar bright features in a magenta ellipse in the center image, and you can see that they kind of look like an island of radar bright pixels in a sea of static. The other observation is if we look over at the left-hand side on the cross-section density as a function of delay plot, where I'm showing you the OC opposite circular and SC same circular polarizations, we see that also over this region, SC starts to dominate OC. So that would mean that the circular polarization ratio is greater than 1, so CPR is greater than 1. Those two properties of these regions are what led the first observers in the early 90s to suggest that these are places that might be hosting water ice because they're very reminiscent of the type of radar echoes we get back from the Martian South Polar deposits and the icy moons. Later observations and measurements by the Messenger spacecraft provide even more evidence that these are likely ice-hosting regions on Mercury. We decided to revisit this to see what else we can do with the radar data, specifically matching radar with those messenger data. Because with the high-resolution messenger topography, we can now calculate the local radar incidence angle, accounting for that local scale topography and geology. And on this map, I'm showing you the simulated campaign average incidence angle map, where blue is 40 degrees and yellows are 85 degrees. This also provides us with important context. In these white areas, those are areas that would be radar shadows. So we don't expect radar return from those points. So this would let us compare against our radar data and see if we didn't see a radar return from these craters, is that something that we expected, or are those craters actually not hosting a radar bright feature? The other thing we could do is we could cross-correlate this incidence angle with our radar measurements and put that through scattering models to better understand the properties of these features. That's what I'm showing you an example of here in this graph made by Mercury, giving you the OC backscatter coefficient model as a function of incidence angle. And here Anne is specifically demonstrating two properties of the terrain that goes into producing that overall model, the surface undulations in red and subsurface scatterers in green coming together to generate that overall black line and comparing it to the lunar scattering model. And so with this in mind, we can then revisit the radar data and see what type of physical properties can get us to the type of observed scattering. So to do that, we took our radar data, we converted it over to latitude longitude from delay and Doppler, and then reprojected it into a polar stereographic projection, which I'm showing you here as the SC radar backscatter map. I'm also highlighting the 5 largest craters in that region. Now here we want to specifically concentrate on those radar bright features. In order to automate that process, we use the dbScan algorithm. dbScan stands for density-based spatial clustering for applications with noise. And all it does is identifies significant clusters of signal in data that is noisy. To verify that this technique worked, we then took the identified radar bright features and overlaid them onto a PSR map of Mercury. In this map, you're seeing PSRs highlighted in that cyan color, and wherever there's a radar bright feature and a PSR coincident with each other, that's shown here as that brick orange color. So we can see that wherever there was a radar bright feature, that is associated with a PSR. But we're also seeing that not all PSRs are associated with a radar bright feature. But we need to keep in mind the context from that previous image, that simulated radar incidence angle. Because craters like Subcoda and Burke, which are 2 large PSRs, we wouldn't have expected much radar return from there. However, craters closer to that radar illumination direction, which I'm showing you here as the magenta arrow, those craters there that are still cyan, we should have seen inside of them. And so those are not occupied regions in terms of where there might be water ice. The next step is then to look for variations in the radar backscatter. In order to do that, we implemented a k-means clustering algorithm. What k-means does is that it clusters data into groups by minimizing within-cluster variance and maximizing the distance between the groups. And so what this does is it allows us to say that certain values are significantly different from others. So in this plot on the left-hand side, what I'm showing you is that K-means class map, where yellows and oranges are high SC and blues are low SC backscatter. But although we fed this information only from the SC, we also see that there's an association with CPR. Yellows and oranges are high CPR and blues are low CPR, typically about equal to 1 or a little bit less than 1. The other observation that we found is that some craters like Chesterton, Tragvedador, and Tolkien can be well described by a central bright feature that is then surrounded by less and less backscatter. And then other craters like Kandinsky and Prokofiev are having more muddled appearance to their backscatter. So we take this observation to suggest that perhaps where you're seeing high radar backscatter could be where there's very pure ice that is then surrounded by less and less pure ice. In order to then test this, what we did is we applied the data through a scattering law. The scattering law we used is seen at the bottom of this slide, and on these plots what I'm showing you is the reduced chi-squared fits using the data over the two free parameters, which is C, the shape parameter, and R naught, which is the Fresnel coefficient, which is dependent on the dielectric permittivities. And because we saw a central bright feature that was high CPR and then surrounded by lower CPR regions, we broke the data down to two groups, high CPR and low. For the regions that are high CPR, we find that it could be well modeled by a material with a dielectric permittivity between 3.3 and 4.5. And for the regions with low CPR, they can be well modeled with a dielectric permittivity between 4 and 5.3. So that means that regions where there are high CPR could be regions that are much purer ice, at least with 3% impurities, compared to regions of low CPR, which would be less pure ice, at least 20% impurities. But it's important to note, though, that there is some overlap here between the two models. Dielectric values between 4 and 4.5 could well describe the backscatter. So the next step would be, if there is a difference in ice purity over these regions, then that there should be a correlation between the radar backscatter and temperature. So in a new paper led by Alison Glansberg, they used the high-resolution messenger topography maps to simulate the maximum temperature expected within Kandinsky, Chesterton, Tragvedador, and Tolkien. I then cross-correlated those maximum temperatures over to the multi-year radar observations that were conducted by Harmon in 2011. And on this plot, you're seeing a nice correlation between radar backscatter and temperature. So really high radar backscatter is typically associated with temperatures less than 110 Kelvin, which would suggest surface ice can be stable there. And then low backscatter is associated with temperatures typically much higher than 200 Kelvin, so no ice is expected there. So perhaps there is differences in ice purity over these regions. But there's something else that we picked out from this, and that is that intermediate class, which I'm going to call class 3, if you plot it over those craters, that corresponds to the cyan color. That intermediate class is about half as bright as the brightest class there, and about 3 times brighter than the background class. So this can't be pure ice, but it also can't be dry regolith. But it's inside of these PSRs where stable surface ice could exist. And when it occurs outside, it's also typically associated with those magentas and purples, that high radar backscatter. So this is a class that is not correlated well with the thermal environment, and due to its brightness, it might be deeply buried ice or dirty ice. What's interesting about this is that this would be the best analogy we have for Mercury for the moon, because on the moon we expect deeply buried ice that would be pore-filling, so dirty ice. The next lesson learned for the moon is that CPR is not a robust diagnostic of ice deposits. On a spot, I'm showing you circular polarization ratio as a function of incidence angle, and you see for the two terrains, the background terrain, the polar deposits, it'd be very difficult to just using CPR to tell which one's which. But if we follow the suggestion by Ann and Sriram in their 2019 paper and look at the polarization separately, we see that the two terrains separate out really nicely, and you could tell the background terrain versus the polar deposits. And so moving forward, it would be better to use the OC versus SC plot instead of CPR. And with that, I'm going to say thank you so much. I'm going to leave my conclusion slide up here for you. And I'd also like to thank the amazing Arecibo staff for their many years of support for the planetary community. Go #TeamRadar.